Okay, so today we will be discussing about the combined uplink and downlink ratio. Okay, wherein in previous classes we had discussed exclusively with respect to downlink and exclusively with respect to uplink. So these are denoted, okay, in the form of U and D, right? And we also discussed about the back off concept, the input and output back off concept, which is very important concept to be considered, okay, because we need to make sure, that our outputs are falling in line, okay, our outputs are falling in line. Sometimes what can happen is there can be possibilities um, that the lines are not proper. So when I say the lines are not proper, these output lines are actually getting saturated. Okay, so you can see at this point of time, okay, they are linear. So I want my responses to be as linear as possible. I do not want them to bend. I do not want them to be stable. Okay, instead I want an output in such a way that it keeps on increasing. So what I will do is I will try to reduce my input, and I will try to bring them in that range, so that my output doesn't go beyond the point here. Okay, so that is called your back off. If it's done to the input, then it's called an input back off. If it's done to the output, then it's an output back off. So the main relation between both of them is you can add about 5 dB. Okay, you can add about 5 dB to the input. So that is nothing but output plus 5 dB is your input back off. So this is how both your input and output back off are related to each other. Right. So I hope all of you are able to see my screen, right? Can one of you confirm?
Yes, sir.
Okay, thank you. So back off
Yes,
is
sir.
one such, thank you. So back off is one such important thing where we try to drive our output in such a way that it doesn't go um, uh, beyond the point which I do not want. Okay, so we are concentrating on our point of interest. Okay, fine. So it's always a good practice to tabulate things and bring them in the form of tabulation, so that you will not have any confusions during your problem solving scenarios. Many times what is going to happen is you will have to remember these constant values, which is like about 228.6. All this you will have to remember. Okay, but make sure that you put them in the tabulation form, and just be aware if it's in dB form or dB watts or decilogs, and appropriate conversions are to be done if required. Okay, so the best thing that you can do is try to get the data from your question, and ultimately you will get to know as to what details are given, and you will be able to fill in those details, and the problem becomes very simple. Okay, more or less here the problems that we see is all with respect to substitution of values. Okay, so when I say substitution of values, see for this example, okay, EIRP value is directly given. Okay, you don't have to calculate it, and your gain is also directly given, which is about 50 dB. So directly you just substitute, and then your TFL, okay, your feeder losses, transmitter feeder losses, are also mentioned as 2 dB. Okay, so that is also directly taken. So ultimately what you have to do here is try and understand the question, try and understand as to what data is given, tabulate them, and ultimately you can just use the formula, fill in the data, and it's going to be as simple as it is. So today we will concentrate on getting both the parameters combined, which is your uplink and downlink, and we term them as your combined uplink and downlink. So in short, sometimes it's also referred to as CNR. The complete satellite circuit includes an uplink and downlink. Now, we cannot just have a circuit which does only the uplink operation, or we cannot have a circuit which does only the downlink operation. We need to have a combination of both. We need to have the base station as well as the satellite receiver, okay, where the signals transmitted from your base station are to travel, and it has to reach the satellite, and proper communication has to be done. So this is actually, the importance of having a TT&C. If there is no communication happening between the base station and satellite, then rest assured, okay, it is going into a graveyard. Okay, so controlling the satellite, having a regular check on the parameters, checking if the batteries are fine, the charging cycles are fine, all these are to be kept in mind. Okay. Right. The complete circuit, okay, you can actually check in the upcoming figure here. Okay. So we will look into this in a while. And noise is introduced on the uplink and the satellite receiver input. Now, can someone tell me what kind of noise is this? For those of you who were in my yesterday's class, you can actually tell me what noise is this, which is getting introduced on the uplink and which is at the which is at the receiver input of the satellite. What noise are we talking about? Which kind of noise is getting introduced?
Antenna noise.
Okay, antenna noise. We are specifically targeting at a device, some device.
Amplifier.
Yes. What kind of amplifier? You're getting it. What kind of amplifier? Traveling. Try to recollect traveling wave tube amplifier, right? So because of this TWTA, okay, this particular noise is going to get introduced at your receiver input. Fine. Denoting the noise per unit bandwidth by PNU, okay, noise and power per unit bandwidth, so PNU, and the average carrier of the same point by PRU. Okay, so the carrier to noise ratio on the uplink, okay, we denote it as U, and carrier at the numerator, okay, and the noise at the denominator, and which is equal to your PRU by PNU. Okay, both are with respect to uplink. It's important to note that power levels and not decibels are being used here, okay, because we are dealing with P. P is nothing but your power. Okay, so we do not measure power in decibels, but then we want them in the levels of power. The carrier power at the end of space link is shown as PR. Okay, so you should be referring the diagram. Okay, so this is your PR. Okay, this is the noise that is getting introduced, and this is your transmission that happens, and the amplification that happens. Okay, these are nothing but your antennas. Okay, the transmitting antenna, the receiving antenna, then the noise that gets introduced, traveling wave tube amplifier. Okay, the noise that gets introduced at the receiver, and then this is about your downlink. Okay, from this satellite antenna, the signals are transmitted to our base station, and this PR is what we are talking about. Okay, so the carrier power at the end of space link is shown as PR, which of course is also at the received carrier power for the downlink. This is equal to the gamma times of carrier power input at the satellite, where in the system power gain, a satellite input to Earth station output is shown. So here, if we model this just in the form of block diagram, okay, you can just see here we have taken the same thing. okay, the gamma, which is actually from this point, the noise introducing point, okay, from, yeah, from this point, okay, and till till we receive this at the base station, okay. So all that happens in this region, okay, is termed as your gamma, okay. And this can be modeled, okay, this can be modeled in the form of a simple diagram here, okay, where the same PRU that is mentioned, okay, is taken up here, okay, PRU, and your PNU also comes here, and the noise, the addition that happens is also mentioned, okay, and these two amplifiers, okay, are together put up, and we have a factor, a multiplying factor called gamma, okay. And at the end, okay, at the end, what we do is here, okay, for this section, okay, we take it as an additive noise, okay, the PND is nothing but your power, the noise power, and your gamma plus PN. So all these factors are modeled, and you can probably take this as a simple block diagram. It's a simple block diagram. Right. So if we model this in this fashion, okay, we can make sure that our PR, or we come with results that our received power is nothing but gamma times PR2, and your noise, okay, is a factor of two terms. Right. It includes the satellite transponder and transmit antenna gains, the downlink losses, and the earth station receive antenna gain and feeder losses. So these feeder losses are nothing but your TFLs, okay, transmitter feeder losses. The noise at the satellite input also appears at the earth station input multiplied by gamma. So whatever noise is there at your satellite input, that also appears. Why is it appearing? Because it is transmitting, and it is getting also amplified, right? Noise is here, noise is getting into an amplifier, so which means noise signals are amplified at the first stage. Then again you find another amplifier here getting amplified at the second stage, and then broadcasting down, right? Okay, so we get a combined value, okay, we get a combined value. So the C by N naught ratio for the downlink alone, not counting just this term, okay, but we have to even consider the noise power with the downlink sequence. The power and flow diagram is shown in your B. Okay, so all this flow as to how it is flowing from one point to another, and the modules that is involved. Okay, the components that are involved is also mentioned. Right. So the combined carrier to noise ratio can be determined in terms of individual link values. To show this, it is more convenient to work with noise to carrier ratios rather than the carrier to noise ratios. So we try to identify what is the noise, and then we know what kind of carriers that we are passing through. So it's very easy for us to find out the noise to carrier ratios rather than finding out how much carrier for each noise. Okay, that becomes a more rather complex terms. See, sometimes what is happening is, if we are not able to get a solution at one point of time, we always use the techniques of reverse engineering. Okay, if it's not possible one way, we will try to do it the other way, okay, in the reverse fashion. So ultimately we need results, ultimately we want information as to how much noise and how much carrier is actually passing through, and what means can be done to nullify the noise. Denoting the combined noise to carrier ratio by N naught by C, because we are now referring to noise to carrier, right? This noise to carrier ratio. So that actually becomes your N naught by C rather than having carrier to noise ratio C by N naught. right? So the value or the uplink value by N naught by C, with U referring to uplink and D referring to your downlink. Okay. So ultimately, what we try doing is we try to equate them to the power values, the noise power and the receive power, and we use the values which were discussed, previously. So which means your noise power is adding up with two values, okay, which we saw previously, a fact of your noise per unit bandwidth in terms of power and the noise power for the downlink, okay, and a simple simplification when it's done, okay, we try and arrive with n naught by c. So ultimately what we are trying to say here is we are having a ratio of noise to carrier instead of carrier to noise. So we individually find out for the uplink and for the downlink and combine them both. Okay, so this equation, the equation that you see here, shows that to obtain the combined value, the reciprocals of the individuals must be taken. So it's as good as taking the reciprocal. So instead of taking C by N naught, we are taking the reverse. Looked at in the other way, the reason for this reciprocal or sum of reciprocals method is that a single power is being transferred. So it makes us analyze in a much easier way. Okay, through the system, while the various noise powers which are present are additive. So noise will always get added because they are passing through amplifiers. Similar reasoning applies to the carrier to noise ratio. Now we'll look at a problem here and we'll try and understand as to what we are exactly referring to. So see a satellite, okay, and it's having a circuit where the individual C by N spectral densities are uplink is about 100 dB hertz, okay, and your downlink is 87 dB hertz. As I mentioned previously in my lectures, right, your uplink will need more capacity than the downlink. Okay, the energy, the power that is required for signal to travel from the base station to your satellite is much higher than the power needed for it to transmit from the satellite to your base station. Right. So we get back to the formula in naught by C, okay, which is equal to, so keep in mind here, we are converting them, okay, because it's in dB hertz. So as I told you, we divide it by 10 and take it to the power of 10. Okay, so 10 raised to minus 10 plus 10 raised to minus 8.7. So once we do this, okay, we will be getting it in the form of your dB. So C by N, okay, will be equal to minus 10 log. Okay, this is the normal conversion that we do, minus 10 log, okay, and the value. So ultimately, we are looking at 86.79 dB hertz. Okay, so this is my combined carrier to noise ratio. Okay, so these conversions you have to keep in mind and just check in what values they are and accordingly add the conversion factors. So this example illustrates the point when one of the link C by N ratios is much less than the other, the combined ratio is approximately equal to the lower one. So here you can see, okay, we had 100 dB hertz and the other one is 87 dB hertz. So your combined ratio is actually equating to the one which is the lowest. Okay, it is not taking up the values of 100 dB, but it's approximately equal to the lowest value. So this applies when we are using our combined C by N ratio, right? The downlink C by N is usually less than the uplink, and in many cases it is much less, as I mentioned just now, right? This is true primarily because of the limited EIRP available from the satellite. So there is less um, um, EIRPs. Okay, so hence you can find that it is very less for the downlink, right? So we will see an example here. A multiple carrier satellite circuit operates in 6.4 gigahertz bandwidth, okay, with the following characteristics. So your flux density, okay, flux density is denoted by psi, right? Is about 67.5, and your back off input back off is 11, and your G by T ratio is about 11.6. So this is for your uplink, and for your downlink also few parameters are mentioned, and they want us to find out what is going to be the parameters, the combined value. Calculate the combined CNR ratio. Okay, combined carrier to noise density ratio for both the links, and the combined value for uplink and then for downlink, and then add them both. Then you will get a combined uplink plus downlink ratio. Right. So in cases like this, as I mentioned, you can take out the values and tabulate them separately. Okay, because there are a lot of values given. You don't mess up with the values when you tabulate things. As in previous examples, the data are best presented in tabulation form, and values are shown in decilogs. Keep in mind, it is always a good habit to mention what kind of values is it referring to. Is it in dB or is it in decilog? So this is a very important step to follow, right? So saturation flux density is given then at 6 gigahertz, and the back off is also given G by T ratio. K is constant, your Boltzmann constant, right? And your C by N, okay, you'll be getting from the equation that we discussed previously. Okay, you'll be getting, once calculated, you'll be getting about 101.5. Similarly, you'll be calculating for the downlink as well. Okay, as you can see, the K used is the same, right? It's the same, and different parameters are mentioned here for your downlink. So what we have to do is, you will have to calculate the noise to carrier ratio. Since it's in the decilog format, okay, we will have to convert them. Okay, divide this by 10. Okay, so it becomes 10.15. Okay, to the power of 10. Okay, so and similarly 9.32. Okay, will be taken to the power of 10. And similarly, when I do a combined, okay, when I do a carrier to noise ratio, I'll be using a 10 log, and to the same value I just bring it down. Okay, and the values that we will be getting is about 92.6 uh, decibel hertz. Okay. So you can see that it is approximately equal to the value which is your downlink. So this is one easy way to cross check if the calculations that you have done is proper or not. Okay, so approximately it will be equal to the lowest value. Okay, fine. Again, it is seen from this example that the value is close to the lowest value, which is the downlink value. Okay, so far only thermal and antenna noise has been taken into account when calculating the. See, as I mentioned, there can be different parameters contributing to the losses. Okay, so as research and development happens, okay, they keep discovering that errors can happen because of what kind of antenna that is used, the way that these antennas are positioned, what kind of quality is required, how it is to be positioned. Okay, all these will be mentioned. Okay, right. Um, Another source of noise to be considered is your intermodulation noise. Okay, so can someone tell me what is intermodulation? So if we have multiple modulations happening, okay, um, intermodulation can also cause a noise, okay. So that's in the form of your ISM, right? So with this, we actually end our third module, and in our next class, okay, we will be moving on to module 4, okay, which talks about the earth segment. And here, most of them are only the block diagrams, okay. So it's going to be as simple as it is, where you have to just draw the diagrams, block diagrams, and explain the concepts, okay. Right. So these were the concepts that we discussed so far with regards to noise, okay, with regards to the antennas parameters, okay, with regards to the temperature, and EIRPs, uplinks, downlinks, and combined CNR. Okay, then your PWTA, very important factor to be considered with respect to satellite, right? Tabulation of values, okay, back of concepts. Okay, so all these you will have to remember in a proper way. Okay, so students, any doubts? Do you have any doubts with the concepts that we discussed so far? Yes, any doubts?
No, sir.
Okay.